The first integration technique we're going to learn in Chapter 7 is integration by parts. So integration by parts is to do integrals that are something like this. X sine x dx. These are integrals of the form some function times another function, right? So we're looking at something f of x, g of x, dx. Now, the first and most important thing to remember when you see this, it is not right to just take the integral of f of x and multiply it by the integral of g of x. Of course it's not, because the derivatives don't work that way either. For derivatives, we had to use the product rule to take the derivative, so it was complicated, right? If I write down the product rule, I've got d dx of f of x, g of x, right? And then I would do the derivative of the first times the second plus the first times the derivative of the second. So in order to take the derivative of a product, we had to do this thing. So now if we're going to find an antiderivative of a product, you can tell that it's going to be more complicated than just this. So don't do this, because it's totally wrong. Okay, so how do we do this? How do we get what we're supposed to do? It comes out pretty quickly from this product rule. If I just take the integral of everything here, right? This, by the fundamental theorem of calculus, the integral of the derivative is just this bit itself. So I get f of x, g of x is equal to those two. So I'm going to rewrite these two real quick. I'm going to write them properly. And all we do is we're going to rearrange this. We're going to keep this one on this side. We're going to throw that one on the other side. And we're going to rewrite it. So let me rewrite it up here. The integral of f of x, g prime of x is then equal to f of x times g of x minus the integral of f prime of x, g of x dx. Right? Okay. So that's actually kind of a mouthful to remember. So we do have a shortening of it, which I'm just going to put up here. I'm going to leave it there for the rest of the lecture. We're just going to use u as f and v as g. So u dv equals uv minus the integral of v du. So this is the shortening for integration by parts. That's what I remember, and that's what I use. I only do this when I'm figuring it out, in case I need to figure it out. But once you've done a couple of these, this is something that's pretty easy to memorize just by the fact that you're doing it. And I will tell you, integration by parts is one of the most common techniques of integration in this class. For most of the things that we're going to do, integration by parts, very common. U substitution, very common. The other ones are more, are perhaps, I mean, you use them, of course, but these are really very common. And in other classes and in the rest of your life, those are very commonly used. So a lot of integrals you can do with this stuff. So let's go and use this. Let's use it with our first example, x sine x dx. And I'll show you how I figure out, or how I set it up to use this. Okay? Because the first thing is that we have two functions. This is this left-hand part. This is u dv. So I have to let some things be some things, right? I have to let one of the functions be u and the other function be dv. So in this example, I'm going to let u be x and dv be sine x dx. And we'll talk about why I chose those two that way after we finish the problem. Okay? Now, what I need for the rest of this, I need v and I need du. Well, du is easy. I just take the derivative of u, right? And for v, I have to take the antiderivative here, right? Because this is dv. So I take the antiderivative. I want to get minus cosine of x, right? Because the derivative of cosine is negative sine. So you can do this if you want. You can write it out somewhere. The integral of sine x dx is minus cosine x. You don't have to do it that way. Sometimes it's going to be something that might take a little bit of integration. But a lot of times this is something that you can do in your head. Okay? So now we have everything we need. All I need to do is put it into this form. So if I put it into that form, I've got u times v, so that's going to be x times minus cosine of x minus the integral of v du, which is going to be minus cosine x dx. So I still have an integral to do, but this integral now is just the integral of cosine x. I know what that is. That's sine x. That's easy. So I took an integral that was more complicated, and with this procedure, now I have it equal to one term here, and then a less complicated integral that I can then go ahead and integrate easily. So minus and minus makes plus. So then I'm going to be down here, minus x cosine x. The derivative of sine is cosine, so plus sine x, and I don't want to forget my c. Okay, so that's sort of a very standard example of where you would use this kind of technique. All right, you're always going to be looking, if you see something where there's two different kinds of functions like that, multiply by each other, right? I've got an algebraic function, a polynomial, multiplied by a trig function. When you've got that, a great place to start is by using integration by parts. Okay. Before I stop with this example, I do want to go over that other thing I mentioned. Okay, what if I had done it differently? Because I chose this to be u and that to be dv. So I have some other choices, right? I could have done, let's see what happens if I do u equals sine x and then dv equals x dx, right? So derivative of sine is cosine, and the antiderivative or the integral of x is x squared over 2. So if I put that in, I'll just do it down here real quick. I have x sine x dx. It's equal to uv minus the integral of v du. Now this is still a true statement, but rather than making my integral to evaluate simpler, I've made it more complicated because now I have more x's. I've got x squared there, x squared cosine x. So if that happens, it's a good indicator that maybe you made the wrong choice here at first when you made your choice of which one is u and which one is dv. And then you just go back and redo it with a different choice and see if that helps out.